I'm sure that in your entire math career, this is not the first time you've seen points on a number line. And maybe you've seen before now that there can be a difference between a filled in point and an open, an unfilled point. If I shade everything to the right, and notice when I'm shading, when I get to the end, I fill in the arrow tip as well to indicate that the shading would continue forever in that direction. The shading is X. The shading is your variable, okay? So if we're looking for X here, X is everything to the right of 5. It's everything greater than 5. X is greater than 5. And when we have the point filled in like this, that actually means greater than or equal to. The one that's not filled in, that's just normal greater than. It means that 5 would not be a solution. The fact that 5 is an open circle is showing us specifically 5 is not shaded. If 5 was shaded, if we could be equal to 5, then the 5 would be filled in. We could be equal to 5. So here, X is everything greater than 5, but not equal to. The shading is X. X is greater than, but not equal to 5. So maybe you've seen filled in an open circle before, but what I'm here today to tell you is that filled in circle can also be represented with a square bracket facing the direction of the shading, so that this would be a left, an opening bracket, and then this is the inside stuff. And the open point, that one can be written as a parenthesis. Again, facing the direction of the shading. The shading would be inside this open parenthesis. That's the starting point. So let's think about this square bracket, this parenthesis. And square bracket will go the other direction. So this, the shading is everything less than -2. X is less than -2. It's not equal to because it's a parenthesis and not a square bracket. Here, the shading is everything less than 5. The shading is X. X is everything less than, 3, not 5. The shading is everything less than 3. x is everything less than 3. X is less than 3, but it's also possibly equal to 3 because this is a square bracket. Square brackets are the or equal to. So why am I making a big deal of showing parenthesis and square bracket when we already have a perfectly good open and closed circle system? Well, it has to do with this thing I said I'd show you, this interval notation. Let's say we had 2 is less than x is less than or equal to 7. On a number line, if we just used our open circles and closed circles, we would have an open circle at 2. We would have a filled in closed circle at 7, and x, the shading, would be everything in between. But not equal to the 2, yes, possibly equal to the 7. If we did it with our new symbols, 2 and 7, a parenthesis and a square bracket. I'm going to copy this down here. A parenthesis and a square bracket at 2 and 7. Filling in everything here. This shows us directly that we have an answer, the interval from 2 to 7 with a parenthesis on the left and a square bracket on the right. This is the answer in interval notation. And this is standard or inequality notation. We can put inequality notation into set builder notation. What is set builder notation? Well, this uses the braces inside braces the set of all x such that vertical bar x is between 2 and 7. So the inequality isn't a set itself. The inequality can be used in a set, in set builder notation. Interval notation, that is a set. I underlined that twice and the emphasis got lost. There we go. That is a set. So this is why we use interval notation a lot in math. It is a shortcut way of delivering this same information about a set with just endpoints. It gives the left endpoint, it gives the right endpoint, and then whether it's a parenthesis or a square bracket tells us if we include or don't include the endpoints. So you might have noticed I was doing graph examples that were just x is greater than, x is less than. And when I jumped to showing this, I went to a compound inequality. I went to one that had 2 numbers. And the reason I did that is because it was easier as a first example to do one like this. What do we do when there is only one endpoint, though? So I was showing something like this. This is x is greater than 3. I can see the first endpoint is a 3 because it's an opening parenthesis. But what do I put here? I don't have an endpoint because it goes on and on forever. Well, going on and on forever in the positive direction is the concept of infinity. And infinity always has a parenthesis, no matter what is over here. So if this was a 4 and it had a square bracket and it goes this way on and on forever, the square bracket goes with the 4, but the infinity always a parenthesis. And this would be x greater than or equal to 4. Or in set builder notation, the set of all x such that x is greater than or equal to 4. Inequality, set builder notation down here. But what we're going to use most often, interval notation. If we had a number line with everything shaded, that would be going to infinity on both ends. Oops. That would be all real numbers. And this negative infinity, that's what we use for infinity on the left side, going in the negative direction forever. So this here, we would have a closing endpoint, a second point of -2. It would have a square bracket with it. But since it's on and on forever to the negative direction, it's going to begin with a negative infinity. Negative infinity always takes a parenthesis. Let's do another compound. If in set builder notation we are given the set of all x such that x is between -4 and 2, including the 2, what would this be on the number line? What would this be in interval notation? Well, the number line between is always leftmost value here, rightmost value here. We are not including the -4. We are including the 2. And I like it with the parenthesis and the square bracket, so we can jump straight to parenthesis, square bracket, -4 and 2. So there's interval notation, the interval from -4 to 2. This interval is a set. Okay, so I'm not drawing the MasterCard logo. I am drawing two sets, a set A and a set B. And notice they have an overlap here. By the way, whenever we draw circles, and look how they overlap to represent sets, this is called a Venn diagram. So we have this Venn diagram here of sets A and B. And this part here, where A and B overlap, this is called the intersection of A and B. The symbol for the intersection is an upside down capital U. When we see the intersection of A and B, what this means is, where do the two sets overlap? What are the elements in common? So let's say A is the set 1, 2, 3. B is the set 1, 3, 5. What is the intersection of these two sets? In other words, what is the set A intersection B? What elements are in both? 1 is in both, and 3 is in both. So the intersection of sets A and B would be the set 1, 3. Because this set contains every element that's common to both A and B. Intersection is one type of thing. I don't want to say this other thing is the opposite, because it's not exactly the opposite. If it was the opposite, it wouldn't include the intersection. Next, we're going to look at the union. And the union is an actual capital U looking thing. So it is the upside down version of the intersection symbol. Union, capital U, just like the U symbol. Intersection's the other one, that's the upside down U. Union just means join together. So the union of A and B would be all of A mixed with all of B. So here, if A is 1, 2, 3 and B is 1, 3, 5, A union B is going to be the set 1, 2, 3, 5. Every element from A and every element from B makes it in to the final union set. So let's take a look at some larger sets. These were just 3 elements apiece. Let's say we have set A 1, 3, 5, 7, 9, 11. And set B 1, 2, 5, 7, 12. We're going to look for A intersection B, and we're going to look for A union B. The intersection, where they intersect, where they overlap, elements common to both sets. 1 is in both, not 2, not 3. 5 is in both. 7 is in both, not 9, not 11, not 12. So that's it. The intersection is the set 1, 5, 7. The union. Union is everything. If it's in A, it's in there. If it's in B, it's in there. So 1, 2, 3, 5, 7, 9, 11, 12. Every element from A or B makes it in. In fact, what did I say here? Every element from A or B makes it in. What word would we use for making it into here? It makes it in if it is in A and B. So an intersection is an and statement and vice versa. When we have an and statement, that means the overlap. When we have an or statement, that is the union. That's both brought in. So another 20 minutes or so. If you need a break, take a break. We're going to expand this idea. And instead of sets that are listed out, we're going to have set builder notation. So we're going to let C be the set of all X such that X is less than 4. We're going to have D be the set of all X such that X is less than or equal to -2. We are going to look for both C intersection D, and we are going to look for C union D, both of them. Well, let's go ahead and look at the graph. Put that in a little bit better spot. I'll just put it here for now. Deal with these when we get to it. Up top, I'm going to graph C, and below, I'm going to graph D. For that, we're going to need -2, and we're going to need +4. C is X less than 4. So a less than would look like that with a parenthesis, and we're shading the things less than 4. Less than or equal to -2 would be a square bracket, but we're still going to the left because we're shading the things less than -2. When X is on the left, it actually shows us, it points which direction to shade to. So which of these is going to be easiest? Well, they're both pretty easy. The intersection is the overlap. Where do they overlap? I'm going to do this one in green. They overlap right here. From -2 to infinity. So x, let's keep it in interval notation, negative infinity to negative 2. That's going to be C intersection D. Or x less than or equal to negative 2. Or the set of all x such that x is less than or equal to negative 2. Or in this case, because we have a special name for this already, C intersection D could actually just be considered D. C union D, that would be both together. I'm going to circle this in red. Both together, that's all of it. And this right here, D, that's already a part of C. So C itself, x less than 4, or negative infinity to 4, but not including the 4, would be equal to C union D here. Let's do another. If you've got it already, that's great. These next examples, make sure you still have it. If you don't have it yet, or if you're a little shaky, these next examples are really going to clear things up, I think. We have set A. Set A is going to be the set of all x such that x is greater than or equal to 3. We have set B. Set B is going to be the set of all x such that x is greater than negative 1. On a number line, we would need negative 1. We would need 3. I'm going to go ahead and I'm going to graph A. A is x is greater than or equal to 3. I'm going to use red for B, greater than negative 1, parenthesis there. The overlap is the intersection. Where does it overlap? Right here, from 3, including 3, to infinity. The intersection is all of it. This piece is included here, so all of it is just the same as the red one. A union B is just going to be from negative 1 to infinity. The intersection is the overlap, where it overlaps. The union is everything from both jammed together. New sets. A is going to be the set of all x such that x is greater than 0. B is going to be the set of all x such that x is less than or equal to negative 3. So what do I need on my number line to graph? I'm going to need 0, and I'm going to need negative 3. going to go ahead and graph A. A is greater than or equal, or sorry, just greater than 0, not or equal to. So parenthesis, not a square bracket. B, that's going to be less than or equal to -3, less than or equal to. Notice I didn't go below because there's not going to be an overlap here. No overlap means that there is no intersection. The intersection A union B is the empty set. A intersection B is the empty set. What about A union B? Well, we have this piece. We have the -infinity to -3 piece. But we also have this piece. And what we're going to do, I'm going to go ahead and write it down here so I have enough room. A union B is we're going to take the first piece and we're going to take the second piece and we're going to join them with the union sign. And this is another way of saying X is less than or equal to -3 or X is greater than 0. Because a union is an or statement. It makes it in if it's in this one or this one. They both come in. For an and statement, it would only be if it's in this one and this one. The two new hottest clubs are Club Union and Club Intersection. Now, the thing that makes these clubs fancy is that there's not just one list at the door, there are 2 lists at the door. And each club has its own rules. To get into Club Union, you must be on list 1 or list 2. If you're on list 1 or list 2, you get in at Club Union. Club Intersection is a lot more restrictive, okay? It doesn't let as many people in as Club Union. Club Intersection, you get in if you are on list 1 and list 2. So 2 lists at the door. Club Union, to get through the door, you just need to be on one list or the other. But to get into Club Intersection, you need to be on both lists. You need to be on list 1 and list 2. That's what Union and Intersection are. They're just like these exclusive clubs, and they have the exact same rules. For a union, you take them in if they're in one or the other. For the intersection, they have to be in both, first and second. Okay, we have time for some more examples. Let's take a look at the resulting set of negative infinity to 4, parentheses on both, intersection, square bracket 1 to infinity. So what I would do, just like before, we're going to go ahead and look at both of these. The interval from negative infinity to 4, we're going to need 4, 4. And we're going to need 1 for the other one. There is negative infinity to 4. And here is 1 to infinity. The intersection means the overlap. It has to be on both graphs to make it in club intersection, to get in this final answer. So where is the overlap? It overlaps here, with a square bracket on the left and a parenthesis on the right between 1 and 4. What about the union? Well, if we look at the same two graphs, and this time we want the union, then to make it into the final graph, it either has to be on one or the other. And between one and the other here, everything is covered. The answer here, all real numbers. Negative infinity to positive infinity. We saw that something like x greater than 4 which could be graphed as this on a number line with an open circle, or a parenthesis with everything to the right of 4, everything greater than 4 shaded, because the shading is the variable, and everything to the right of 4 would be the variable being greater than 4 to the right of on the number line. We also learned that if we had x less than or equal to -2, that would be either the filled in circle point or a square bracket with everything to the left being shaded, everything less than. And now these are both on the same number line. We saw in order to actually join two together, that's a union. That is an or statement. So the fact that we see both of these together means that we are taking them both together. We're taking the union. We have an or. Here, if this said and instead of or, then actually it wouldn't exist at all. Why? Let's imagine Let's imagine that we had an and statement. And is the overlap. X greater than 4, X less than or equal to -2 has no overlap. So there would be no solution to the and statement. Whereas the or statement would exist. It would just be the two joined together, the union of both. We saw that from a graph. We can clearly take the endpoints and whether it's a parenthesis or a square bracket and use our infinities to indicate both directions forever. Infinities always take parentheses. And if we have two of these intervals and we want to take the union, we use the union symbol. So we connect disjoint intervals with the union symbol. Today, we're going to work with solving inequalities, and then we're going to get our answer in inequality form. We're going to make sure we can put our answers on the number line and in interval notation. So all of that, taking the inequality answer, graphing it, putting it in interval notation, that's from the last time we were together. This time, we're going to use those just in writing our answer. But you need to know how to do that in order to get your answers the way that we want them. So if we had the simple equation x plus 4 equals 0, how would we solve it? We want to get the x by itself, so we need to undo adding 4. We undo adding 4 with subtracting 4. Whatever we do on one side, we do on the other. It leaves us with just x on the left, and then 0 minus 4 is -4 on the right. If we wanted to express our answer as a set, it would be the set containing our answer, one number, -4. Solving an inequality is pretty much exactly the same as solving an equation. And I say pretty much because there is one important difference, but that difference doesn't come into play here. So let's say instead of equals, it was less than or equal to. X plus 4 is less than or equal to 0. You do the same thing, and you get the answer x is less than or equal to -4. Not bad. If you can solve equations right off the bat, you can solve 90% of inequalities. And I pulled that number out of thin air. No one ever has real percentages when they say that. What someone means when they say you can solve 98% of problems using that, they mean most. Great many most. So what's the special rule? What are the ones that we can't solve like that? The rule comes into effect when you multiply by or divide by a negative. The word by is very important here. It doesn't mean any multiplication or division involving a negative. It is only when you have something and you're taking what is there and multiplying it by a negative number, or you are taking what is already there and dividing that by a negative number. That first number can be positive or negative, doesn't matter. The rule only kicks in if you are multiplying by a negative or dividing by a negative. And here's what happens. If you have that, you switch it to that. If you have that, you switch it to that. It is laughably easy if you can already solve equations. So if at this point you're not having any struggles with solving equations, if you are consistently getting the right answers, then all you're going to have to watch out for here is multiplying by a negative, dividing by a negative. And it's not going to be in every problem, but we will do a lot of problems where it does happen because those are the more interesting ones. But every problem is not going to have a flip. This one will. Let's say we have negative 6x plus 4 is less than 34. Well, let's pretend it was equals 34. And let's not do anything differently until we get to a step where we might multiply or divide by a negative number. Okay, so we want to get the x by itself, which means we want to get the 6x by itself, the negative 6x. Well, I can go ahead and subtract 4 from both sides because I want to keep it balanced. That leaves me with negative 6x on the left. Subtracting 4, that's not multiplying or dividing by a negative. So keep the sign like it is. 34 minus 4 is 30. I want to get the x by itself. I'm going to divide by negative 6. Warning, warning, danger, Will Robinson. I was going to say that's an old reference, but by golly, there is a remake, so it could be a more recent reference if you're danger. We are left with x on the left, but since we are dividing by a negative 6, the less than becomes greater than. Positive 30 divided by negative 6. Positive divided by negative is negative. 30 divided by 6 is 5. So the solution to this inequality is x greater than negative 5. On a number line, that means we would be at negative 5. There's no or equal to, so it's a parenthesis. And we want to graph greater than. So it's an open parenthesis with the shading to the right. Our answer in interval notation, we can see from that would be a parenthesis at negative 5, and it goes to infinity. Infinity always takes a parenthesis. So the answer in interval notation, parenthesis, negative 5, comma, infinity, parenthesis. Let's do another. Negative 5t minus 6 is greater than or equal to 24. Let's not do anything differently than normal solving of a linear equation until we run into a step, which may or may not happen, where we multiply by a negative or divide by a negative. To get the t by itself, we've got to get the negative 5t by itself, we've got to add 6 to both sides. Leaves us with negative 5t on the left. Leaves us with positive 30 on the right. Adding 6 is not multiplying or dividing by a negative. The inequality symbol does not change. Here, we are going to divide both sides by negative 5. Danger, Will Robinson. Switch the inequality sign. Positive 30 divided by negative 5 is negative 6. So t is less than or equal to negative 6 on a number line. We have negative 6. The or equal to means a square bracket. And since we want less than or equal to negative 6, it's going to point off to the left. And there's all of our shading. From here, we can see that our interval notation, we're going to start with negative infinity. We're going to end with a square bracket at negative 6. Comma separates. So our interval notation for t less than or equal to negative 6 is going to be parenthesis, negative infinity, comma, negative 6, square bracket.